Hi, and welcome to this second clip in the Born-Haber cycle series. And if you remember the previous clip, what we were looking at was evaluating some of the decisions and some of the definitions which were required to generate the equations and the processes required for the formation of sodium oxide. And we derived a series of equations and processes which were needed to transform sodium and oxygen into sodium oxide. And so what we need to do in this version of the process is put these into a diagrammatical format. And what you'll notice, that is the first half of the equation, and what we have is we're going to try to represent those individual equations which we derived in the first example, but in the first clip, and try to write these now as energy level type diagrams. And so what we've represented there is the enthalpy of formation of sodium oxide, and we've drawn it as a downhill process, assuming that it's going to be exothermic. And we would be able to generate these values from research on Google and also using literature values in textbooks. And so what we need to do now is essentially complete the cycle as we would have done in year 12 with situations such as Hess's law, whereby we had triangles using enthalpies of formation and perhaps enthalpies of combustion. And so what we'll do is we'll first of all discuss the sodium. And if you remember from the previous clip, in the first situation, or in one of the situations, we had to take sodium as a solid and transform it into a gas. Once we transformed it into a gas, that allowed us to then do the first ionization energy, whereby we produced sodium gas plus the electron, which would be required to react with the oxygen in its later stages. And so if we complete off the equation, you'll notice that the oxygen in this situation hasn't changed. We take each process as an individual state and we just look at one species along the way. So in the first step, which actually correlates to equation number 2 in the previous clip, and the second step being to equation number 1 in the first clip, we have taken here the enthalpy of atomization of sodium, and in this one we've taken the first ionization energy of sodium. And what we have to also do is, because we've got two sodiums, we would have done the first ionization energy twice. Numerically, when we get to it and we do a calculation, we would have taken that first ionization energy and multiplied by 2. Likewise, we're going to take this atomization energy and multiply it by 2 in terms of its energetic values. So now we've got sodium in its ionic form, 2 sodium ions. We have to now concentrate on the oxygen. And if you remember back to the previous clip, we had equation number 5, whereby we split up the oxygen molecule into its singular oxygen atom. Obviously we've taken half an oxygen molecule, so we just get the one oxygen atom in that step there. That was equivalent to the 5th equation we had in clip number 1. We then have to use these electrons, which we've got generated from the sodium, and we now have to create, using equation number 4, we have to create, now sodium ion is already created, sorry, this is a gas. We have to now create the first process whereby we have that oxygen 1- ion and we have a spare electron. So we've used one of the electrons to ionize or do the first electron affinity, as we called it in the previous clip, we'll do the first electron affinity where that oxygen has taken on that first electron. And equation number 5 was the atomization, assuming we're using an atomization value for oxygen. If you remember, if we got bond dissociation energy, we'd have divided that by 2. So now we've done that. What you'll notice is, as well, like you do in an energy profile diagram, any value which goes upwards is assumed to be, or is, endothermically processed there, and anything which is coming downhill is exothermic, and therefore will be releasing energy. So essentially we're putting energy in to everything that goes uphill, and we're getting energy out for anything which comes downhill. And so for this step number 4 here, this first electron affinity, what we've done there is we've made a bond between the oxygen atom and that first electron. Making a bond is an exothermic process generally, and so we can have an endothermic process. However, in the second electron affinity, we see that the opposite is true. This is equation number 3 from the first clip. The second process, or the second electron affinity, which we then have here, is endothermic in direction. And this is endothermic in direction when we are manufacturing the O2 minus gaseous ion, because what we have here is we are now experiencing repulsion between the O minus ion we've just created in that first step and the electron which is now going to be trying to added to create that second 2 minus charge. That repulsion means that we have to put energy in, and actually that goes to a more energetically unstable state in that situation. So the second electron affinity is an endothermic process, whereas the first electron affinity is exothermic. And then the step which we didn't discuss in the previous clip is the one which then completes this cycle together. And this is generally the largest step of this process, and this is what will be defined as the lattice enthalpy. This is a new term which we've not discussed yet, and the lattice enthalpy of a substance is the enthalpy, or the standard enthalpy change, for either the separation of 1 mole of the ionic solid into its gaseous ions, or, as I've drawn it here, it's the enthalpy of change associated with the creation of 1 mole of sodium oxide. So technically, the lattice enthalpy can be defined in both directions. However, when you calculate the value, this sign will predetermine whether or not it's going up or down. So obviously, if you are given a negative value, your arrow would go downhill. If you're given a positive value, your arrow would go uphill. And likewise, a question would talk about that, and it would give you more clues as to whether it's going up or down. But you may see those given in either format. To make it easier for what we're doing today, we'll just consider lattice enthalpy as being a downhill process, and the energy which we would receive by the gaseous ions coming together to form that energetically stable ionic solid. And what we will do is we will then move this forward, and we will find the values. Now you could use Google. A question would obviously give you the values in an exam. But what we will do is, in the next example, we will look at a way in which we can calculate the lattice enthalpy for a process. In this process, we will be using the Born-Haber cycle for sodium oxide. And what we will do is we will generate these values, and we'll look at that in the next clip in more detail. So if we will head over to clip number 3, I'll take you through the calculation of the lattice enthalpy.